All right, howdy everyone. Thank you for coming. We are the Halliburton team and we will share with you today what we did for our project. So first, let's give you a quick introduction on what we did this semester.
So for some background about Halliburton, they're arguably the largest oil and gas service and product provider in the world. And we'll be focusing on the product side of things in this project. Halliburton's products need to be rated to endure the intense wellbore conditions they will be subjected to in the field. These ratings are chosen as design criteria during the design stages, but they also need to be validated using physical testing for the clients of Halliburton to be satisfied with the product prior to using it in field use. And usually what this means for Halliburton is finding a way to simulate wellbore conditions in a controlled environment. This requires a pressure vessel that can be pressurized to those wellbore conditions, inside of which a Halliburton product can be mounted and validated for those high pressures. The current way of sealing this test fixture, which is what we'll be calling it from now on, is an elastomer O-ring right now. And these O-rings have a problem in that they can fail in the middle of validation testing. This is largely caused by high temperature cyclic loading that is part of the Halliburton validation procedure. And the reason it's part of that procedure is because it can often be seen in the field. So it's desirable to simulate them in a controlled environment. The design requirements for this task is 0 to 30,000 PSI, 40 to 400 degrees Fahrenheit. And the team will be tasked with a 3-inch design in a small scale setting, and it will see no field use. So to summarize, our task is to explore and procure a new sealing method as an alternative to an elastomer O-ring that should be able to be validated during an entire testing procedure. And we are also to design and manufacture a separate test fixture for our own team use.
So as Tony mentioned, one of the biggest problems with the current sealing system with the elastomer O-rings is that they fail due to temperature cyclic loading. And so what we have come up with is a spring-assisted seal, which is made out of a thermoset plastic rather than elastomer, which is much more resilient when it comes to temperature cycling. So this spring-assisted seal has 3 major components: the jacket, the spring, and the backing ring. And the way it works is, if you'll direct your attention to the photo on the bottom right, as the pressure in the vessel keeps going up, that pressure will push up on that seal and actually provide that sealing force that'll force those 2 lips against the sealing interfaces to create a seal. And the more pressure is inside the vessel, the greater sealing force will be provided. And so the jacket that we have chosen is made out of carbon-filled PTFE, which is a thermoset plastic, and that is that blue in the photo on the top right. And the reason this has been selected is because it has great extrusion resistance. And what that means is, if you look again at the picture on the bottom, that extrusion gap up there on the top is basically a relief for material in the seal to get pushed through whenever it's under a lot of pressure. And we don't want it to extrude too much because that'll damage the seal. And so the second main component of the seal is the spring. And so this spring is made out of stainless steel, and the purpose of this spring is to provide the initial spring force at low pressures. At low pressures, you're not going to have enough force from that pressure to create a seal. So that spring is going to create that sealing force initially. It's in a cantilever shape, which is very useful because it is very scalable. And so since we will be designing a 3-inch diameter seal, it'll easily be scaled up to 14 inches for the big scale product testing. The third main component is the backing ring. This is made out of virgin PEEK. And so you'll see the photo on the bottom right again. That backing ring goes behind the seal and provides structure on the back end of it, and it will actually resist and direct that seal extrusion. So large amount of the time it'll extrude itself through the extrusion gap, therefore protecting the jacket of the actual spring.
Now, once we had our seal design finalized, we then had to come up with a test fixture in order to test this seal. The test fixture we chose to make it out of machine 4140 steel, which is a very beefy steel and has very high yield stress. We went with a modular design. That way we could easily swap out and change the dimensions of the plug in the event that we needed to alter our seal and change it. The collar, as you can see on the left, pictured in the yellow picture, this is responsible for screwing onto the outer part of the vessel and securing the plug in place. The plug is what actually houses the seal, and this is where the interface between the lab equipment and the fixture actually takes place. This is where the high pressure connections screw into the vessel or screw into the test fixture. The vessel then on the right is the main containment body, which houses this main pressure, which also has threads on the outside for the collar to screw into. After we had all our designs, we then went to procure them. We reached out to UTEX Industries, who were very friendly with us. They actually had us come out to their facilities and take a tour of their manufacturing plant. While we were there, we got to actually sit down with their UTEX engineers and discuss with them different sealing methods, and we're just a very good resource for learning there. We ordered 5 seals from them, and then we shortly found that out with the good news that our test fixture was going to arrive around 2 to 3 weeks early. With this extra time that we now had, we decided to go ahead and order another 5 seals. That way we could do additional testings now that our timeline had enough room for it.
And regarding the test fixture, once we started looking at different rows to go down as far as manufacturing our design, we quickly realized that it was going to be quite expensive. So Halliburton offered to manufacture this for us, and they gave us the final cost of what it cost them to have this built, and it was around $5,300 just for one.
So in order to validate our final sealing mechanism test fixture, we have to test them. This is going to be twofold. The first is going to be preliminary interval pressure testing, as we don't know the exact capabilities of the seal that we've procured because it's novel and was made to order. We're going to take our seal and test fixture up to the maximum temperature and slowly increment pressure to determine what that failure point is. Secondly, we'll do cyclic testing, which is what Halliburton uses to validate all of their products and simulates wellbore conditions. So this will be comprised of multiple temperature and pressure combinations, and the seal will have to hold that pressure for 15 minutes at each stage in that cycle in order to be considered a success.
For risk analysis, we did a failure mode effects and criticality analysis, also known as a FMECA analysis, on both the test fixture and the test procedure. And this helped us analyze the risk of the test fixture rupturing or any other issues that could occur during the testing. We also did a fault tree analysis to thoroughly go through the testing procedure and identify any potential failures. And the point of these tests were to identify any overlooked areas or possible safety risks and help mitigate any possible failures. And then in addition, we will provide a safety manual, which will facilitate safe operations of the test fixture and the seal. And the manual includes general precautions regarding the test fixture, pre-test safety inspection and suggested precautions, and as well as precautions associated with the seal.
So initially, the team had planned to do some small-scale validation at Texas A&M. However, due to COVID-19, this wasn't possible. And the team had planned to test on a 3-inch design. And because the way that the seal was designed, this 3-inch design results would be similar to what a 14-inch design result would also look like.
Since all Halliburton's testing equipment is much larger than our test fixture, the full-scale validation will need to retrofit to 14-inch seals. This means if Halliburton follows through with our design to test at their facility on a full scale, they will need to get in contact with UTEX and order larger seals. A full-scale validation would be easier to translate to a real-world scenario since they would be the same size seals used on an active site and not require conformance. So thank you for listening to our presentation. We hope you found our project interesting and learned something about our sealing system.